Thanks. I have an example too of loop fusion and some MLR generation and an optimization too. So coming up. I'm Steve Scalpone. I'm the engineering manager for the NVIDIA HPC compiler group. We're the team responsible for the C compiler, the C++ compiler, and the Fortran compiler, OpenMP, OpenACC, CUDA Fortran. Fit into the bigger compiler team at NVIDIA. And today I'm going to talk about our work, not so much with LLVM that we do at NVIDIA, where we've used it for code generation and low-level optimization and machine-specific optimization, even some vectorization for ARM, for Power, and for x86 for quite some time. But today, just talk about flying. So if we look at Fortran, it's a pretty old language. It's been around for a long time, and there's a lot of codes written in it. The language that we start with in flying is Fortran 66. And there's some features of Fortran 66 that people still use, and we support those as well as there's the base language there. So an extended range loop is a regular loop, and then imagine that there's a goto in the middle of the loop that goes off somewhere else, does more computation, and at the end of that, does a goto back into the body of the loop. Well, that's supported. It's called an extended range loop, and it's defined. The language that we're pretty familiar with, or at least from look and feel, is Fortran 77. And that's where what they called back then structured programming was introduced to the language. And that's things like if, then, else, do and end do, a little bit of structure there before it was all single line statements. And it also introduced the type character. And character is not a single character. It's actually the Fortran version of string, and it has a size associated with it. Fortran 90, often called Fortran 9095 because 95 was a fix-up on Fortran. That's where modules were introduced, and that's pretty similar to C++ modules that are in now. It's a way to define the interface to program, and then other program units can import that interface and use it. It gives a little bit of type checking and type visibility between the two. It also really changed how array handling could be handled, and arrays were extended quite a bit there. Also introduced allocatables, and allocatables is a way for Fortran to allocate entities on the heap and or on the stack, and then at the end of their lifetime, they're automatically reclaimed. There's no garbage collection, but there's no memory leaks in Fortran either. 95, there were minor revisions, but what they did is a mass obsolescence. So they picked many features back from Fortran 66 or 77 and said, these no longer need to be supported. We'll talk more about that in a second. Fortran 2003, that's another thing I'll be talking about a little bit in the rest of the talk. It's where object-oriented support was introduced, classes and polymorphism, and also parameterized derived type. In Fortran, a derived type looks a lot like a C++ struct. Parameters lets you pass in things like type or length, and you can use the type to say what, as a way to configure the types inside the derived type, or the length to say how long an array would be. So it's a little bit of generic programming there. 2008, the big upgrade there for parallelism. So with coarrays that Troy touched on a little bit, and do concurrent, which is a way to execute the iterations of a loop at the same time. Also introduced submodules. Well, modules up here that we talked about, they were only one level deep, and submodules makes them 2 levels deep. So you can get a little more compartmentalization of your program. And in 2018, another revision where parallel teams were added to coarrays, and it's a way to coordinate the different images that are running at the same time. And they also did a lot of work. There's always been a bind C option, a way to expose things to C programs, or a way to access things in C programs between Fortran and C. And what the 2018 standard did is it added a lot more support for getting at the information about arrays and objects in Fortran, or constructing those in C, to make C programs able to take advantage of features that were announced, say, in Fortran 90 or Fortran 2003, which is pretty cool. But I did talk about the mass obsolescence, and obsolescence is sort of like deprecating a feature. And one thing about Fortran programmers is they don't really sign up to that. They expect that existing code, if they can find it and if they're using it, will continue to compile and will compile for a long time. There's Fortran 77 libraries that are still maintained and use obsolete code or deleted code from the standard, and people expect those to work. And the way we handle that in Flying is if the feature doesn't impact something in the current standard, then we support it. And that's most features of those old languages. So if we see that someone's using it, we add support into the front end to support it. We have an option that says enforce the standard, where those extensions or deprecated features are called out. Maybe it's not implemented perfectly everywhere, but for the most part, that's our intention, that you could use it for a standard language compiler or to bring in any of these old features. There's a code called LAPACK, which is very popular, very common, used in all sorts of code. It's a linear algebra and basic linear algebra package. And if you download it today and get the current version, there's a couple of features that have been deprecated for quite a long time. Statement functions, which are sort of like inlines, and equivalence, which is a way for memory to be overlaid. So it's a little bit like a union, but a little more control of exactly what's getting overlaid with what, which is a feature of Fortran. I won't go into that anymore. Let's take a look at some code generation that we're doing right now in Flying. We'll take a look at some basic flows. So one thing Fortran has is called alternate returns. An alternate return, you can see in this code here, here's a subroutine. And these stars represent parameters that are labels. So when it's called, you call it with a label. And then if it says return 1, returns to the first label, say return 2, returns to the second label, just say return, it goes to the next statement, just like you'd expect. So what I was showing with my laser pointer that you couldn't see was alternate return is these stars are labels that are passed into the subroutine. And then if you say return 1, returns to that label. If you say return 2, returns to that label. Here's a call. There's star 5. There's 5 as a label. 7 is a label. So it's kind of interesting, like a beginning attempt at exceptions back from Fortran. And here's the FIR. FIR is the intermediate language that we generate. It's a high-level dialect of MLIR that maps pretty closely to Fortran. So a lot of the Fortran features go right into FIR, and what we wanted to do is have an incremental lowering from AST into FIR, then for FIR into MLIR, standard dialects, then into the LLVM dialect, and then into LLVM-IR. And each one of those could do a progressive lowering. And to simplify things, also to provide many places for optimizations to hook in. So what we can see here is there's the FIR call right there. There's the call to S. And then there's a select, and the select is like a switch statement where it gets back the value 1, 2, or the default, and then it branches to the different branches. So it's pretty straightforward IR. Nothing special there. Here's the callee's code. And the callee is loading some values, then gets the result. And as it does the branches, it loads the 0, it loads here's a constant 1, here's a constant 2, and then here's the return right there. So you can study these more if you want. It's a sort of an eye chart. Entry statements. In Fortran, you're allowed to have a function. Here's a function. But you can also define other entry points where someone can call it externally with different arguments and even potentially different return types. In this case, it's all the same return type, which is a real. And LLVM does not support entries. So there's just one entry with an external on a subprogram. So typically what we would do is implement it one of two ways. One is you would implement a stub for each of the main function at each entry, and then have a main routine that takes all of the arguments, and then a switch inside that says go here, go here, go here. But what we choose to do for flang was to do function cloning. And function cloning might end up being interesting for as a main ways to do inlining or specialization of functions. So we thought we would do it like that. And what cloning does is it basically takes this function again and plays it out again with a new name and puts a branch at the beginning to the entry point. And one interesting thing is that a variable that has a save attribute, that's like a C static, those have to be globalized because that value has to be shared between each instance. And so here we just show it again in Fortran, where we've created a new function for R1, stuck a goto right at the beginning that branches to where the old entry point was. Then it runs through and returns just as if it was the entry statement. And then we'll just count on the fact that dead code elimination will remove all the other branches that don't get executed. And then here's this variable, and we've globalized it. So we've taken it out of the function, made it still a stave variable, and the code would be rewritten to use that as well. Let's take a look at the evolution of arrays in Fortran. So that'll come up in the example. So Fortran 77 arrays, back in Fortran 77, an array was pretty much represented just as a base address. And it was up to the callee to decide the shape of the array that was passed in. They had really no hint in the array from the caller about what its shape or size or dimensions was, and there had to be a handshake between the caller and the callee. And you can see here some declarations. That's just standard. The lower bound here is 1 in Fortran, so it's 4-element array from 1 to 4. You can specify different bounds, so this is -3 to 3. And you can have multidimensional arrays. Arrays are first-class objects in Fortran. Multidimensional arrays are first-class objects as well. Here it's -3 to 3. Here it's 1 to 7, and then 6 to 7 for the third. You can also pick up the dimensions from the parameters. So here's the lower and upper bound. We're just taking those from parameters. Here's 1 to m and 1 to n, a multidimensional array. And again, it's just passing in the base address, and then it's up to the callee to decide what the shape of that array is. You can also have assumed size arrays where the bounds are default to 1 but aren't necessarily passed in, and you can just address those forever. And it's always the last dimension that is the boundary that can be unspecified there. So look at a simple example of that. We have a call here in this lower defer. It's where we allocate the array, and here it's 100 32-bit floating point numbers. Then we do the call, pass it in, and that's basically it. Pretty straightforward. Now, it didn't have to be, it could have been changed to, if we didn't pass in the bounds, we could have done that as well. Now let's take a look at what happens in Fortran 90 and Fortran 95. What happens there is that they've introduced array valued expressions. And those expressions are created with bounds and strides in each dimension. So now the caller or the creator is responsible for giving all the information about the array itself. And so arrays are represented now as a base address, like they were, plus extra information, and that's known as the descriptor. You may have heard it as a dope vector, but it's a little richer than a basic dope vector, and it's called a descriptor. Then the other thing that happened in the language is allocatables, dynamically allocated arrays. They're often on the heap, but they can also be allocated on the stack. It's implementation defined, and they are, when they go out of scope, they're deallocated. So we see here our function is called S2, and this bound right here with the colon means that the bounds are inherited from the parameter. Then you can see here's one that's fixed. Now this will be the calling routine. This 100 right here, that's 100 reals, and it can be just passed in. But we also introduced the notion in Fortran of a section. So here's a section that goes from 4 to 40, so 36 entries, and it's stride of 2. So it's every other one, and it's passed in, but when it gets here, it just looks like a regular contiguous array, even though it's not. The descriptor has all that information, and the routines use the descriptor to do all the addressing. Then here's an allocatable 40. Just pass in the D, and it knows here in subroutine S2, the dimensions, the lower bound is 1, the upper bound is 40. So now we know we have a lot of information passed in about each array. Here's a pretty simple example where we're going to build up some dimensions here with gendims. So there's a constant for the lower bound, the upper bound, and they're put in right there. The stride, we're using that 1 because the stride is 1. Makes the array here where it's taking the 100 by 32 and then using, this is a MLR sort of wildcard. It says it's a some dimension by 32-bit floats. There's a FIR type called a box, which is a synonym for a descriptor. Put in both the array and the dimensions, and then pass that off to S3, the call, S2, and then S2 can get that information, has it in the box here, then it can dereference the box to get the information it needs to do code generation. Fortran 2003 introduced a concept called a parameterized drive type, and the parameters can either be a kind. Now a kind is used to sort of specialize a real. So if you have a real, it could be a 32-bit, a 64-bit, 128-bit floating point number. It could even these days be a 16-bit number. And the kind is often the byte size. It doesn't have to be in the language, but it often is. So a 4-byte real, 32-bit float, the kind is 4. Here's an integer, kind of 8. Again, the convention would be 8 bytes, so 64-bit integer. And that can be passed in when you create a parameterized derived type. And here you see that the kind, whether it's a 32-bit or 64-bit real, can be passed in when you create the type, because this is where you'd specify the kind. Then there's a length parameter, and the length is used for array lengths, and has a special type len. So when it's created, you can pass in the length. Then here it's building 2 matrices that are B by B. Again, it's from 1 to B, 1 to B, like that. There's a couple ways to implement. So what you can see is here that you're going to have a struct type or a derived type that has variable length components, because when it's instantiated, these arrays will be different size. And one way you can implement that is by putting these things in line. Just put the descriptors in line, then you implement the arrays in line, and that gets a little bit complicated. It's sort of a special case, but it's a pretty legitimate way to go. What happens though is all the records of a particular instantiation are the same type, but you can't count on matrix pair impl or matrix pair. They'll be different size for different instantiations. So there's a little bit more difficulty there. So what we decided to do instead in Flang is to convert those to allocatables. And so it's in the source, it's behind the scenes. And when you create an object of matrix pair, behind the scenes, it's going to allocate the 2 matrices as separate allocations and then manage those in the compiler. It's pretty straightforward. Here you can see an instantiation, in case you were wondering. There's K, which is the type. Here's it deferred. This means it's going to build the thing without having to know its size until you actually allocate one. Right there. So arrays, there's a lot more complication than that, a lot more interesting things you can do with arrays. They're pretty cool objects in Fortran. Sometimes I think of Fortran as a DSL for arrays because it's really something. We'll take a look here at an MLIR example of something we do with arrays. So you can have array valued expressions. So think of this as array 1 plus array 2, then the sum multiplied by array 2 again. And the semantics are that these are added, there's a temporary array created, then that's multiplied by A2, then the result is put into A3. And in this case, pretty trivially, we know we can write directly into A3. But what we'd like to do is not create a temporary here and diffuse the loops. So if we write this out in regular Fortran, we see there's two loops. Here's the first addition, then here's the second one with the multiply, then it returns the value back. And so we'll show the generated fir for that. So basically you can see that there's two loops. Here's loop 1, here's loop 2. The dimensions were created up here. And this operator fir coordinate takes a dimension and linearizes that into a regular base plus offset address. So once we have this and we know this is correct, we can check to see if it conforms to what's allowed in the affine dialect. And we check those conversions, make sure that the loads and the stores are all conform to what the affine dialect was. And in this case, it was true that we could. And we converted to the affine dialect of IR. So if you know about MLR, you know that it's a IR that can support many IRs. It's an IR for defining IRs, and sometimes it's confusing because there's an MLIR standard IR, which is called MLIR, and then there's also the framework, which is MLR, and there's an affine and a vector and some more predefined IRs. Plus, there's the one that we use for Fortran, which is FIR, that was defined as part of the Flang project. So we've converted the FIR to the affine, which comes along in LLVM. And an affine apply here, you can see, is the same basic idea as the FIR coordinate, which is taking an array coordinate of base, index, and stride, I guess. Yeah, and turning that into an offset into memory. And then there's the add, and there's the multiply. And one interesting thing about this is that we were able to tell MLIR framework, and it told the affine framework, that the FIR convert operator doesn't have a side effect. So if you see it, don't worry about it, just bring it along and don't let that affect your calculations. Remember, what we're trying to do is see if we can get loop fusion to work, and of course this is a demo, so it worked. And here's the optimized R. You can see that there's just one loop. There's the add, there's the multiply, and there's the store. And I assume if we took this to the next step, it would go through, it would be vectorized, and either by LLVM optimizer or by the vector pass in MLR. And we get some pretty fast code out of that, where we eliminate the temporaries and then vectorize the final result. Maybe even someday we'll parallelize that too. One thing to point out here with MLIR is that you can mix, like I said, the various kinds of operators. So here's an affine for from the affine dialect. Here's some FIR converts from the FIR dialect. And then the addf and the mulf, they're from the MLIR standard base, from the standard base dialect. All right, well, this went a lot faster than it went in practice, so that's great. A number of things we didn't cover. There's all sorts of things in Fortran. We didn't cover how we're doing polymorphism. IO is built into the library. There's IO statements and an IO library. We didn't really talk about expressions, expression lowering, or the math intrinsic library that is in classic Flang, and we're bringing that forward. You can call those routines directly. We didn't talk about the runtime data structures for descriptors or for types. There's a very rich set of data structures that we use, a little like RTTI, but was Fortran specific, to describe the various types, the polymorphic types and the derived types, so that we can implement deep copy, copy, reallocation, freeing, finalization, all with a fairly small set of routines that operate off the data structures. We didn't talk about memory layout. We didn't talk about data statements or equivalence or globalization, how names are mangled, things like that. And none of the parallel features. So coarrays we didn't talk about, or OpenMP, any of those sort of mappings. And that's it. We've flying has been part of a sub-project in LLVM for about since February, I think it's been. We have the code up there, so you can find the code underneath the flying subdirectory. There's a LLVM mailing list that's available to everybody. And then if we look at FIR, when we went upstream, FIR was not ready to be upstreamed. And what happened was that we had about a 26,000 line. We'd rather review that as a series of smaller patches. So the FIR patch has been going on in a different branch. It's open and you can see it. And this is the path. And there's a steady stream of changes coming from FIR being upstreamed into LLVM project. But on the back end, there's a steady stream of changes as people do more and more lowering into the F18 LLVM project. So the size of the diffs is staying about the same, but it's not diverging except in the FIR part where it just increases its implementation. That's it. Thanks, Johannes.
Thank you.